Hello my friends and welcome to my channel. Today we're going to discuss the node voltage method, which is also known as node analysis. So in node analysis, we have a method that is used to analyze circuits, especially DC circuits. Even AC circuits can be used, but by taking advantage of the node voltages as taking them as independent variables. And then one of the nodes is taken as a reference node, which is grounded, and as you know, a grounded node gets zero potential. What you need to remember is that a node is a point or a junction at which two or more circuit elements or circuit branches meet. You remember that a branch is any part of the circuit that consists of either a passive or an active element. Passive elements are elements that consume energy, while active elements are elements that produce energy, such as sources, voltage sources, current sources. So if there's no element, passive or active element in between the two nodes, then that is simply one node. What you see here is two nodes, that is node A and node B. So in node voltage method, we assign each node with a potential, meaning that this node is going to be assigned as VA, which is potential VA, and this node is going to be assigned with a potential VB. So if we have a current flowing through this resistor from node A to node B, it implies that current is flowing from a higher potential to a lower potential. Therefore, for us to determine this value of current, we're going to have the higher potential subtracting the lower potential, which is as shown here. So we have the higher potential is VA in this case, subtracting the lower potential, divided by the value of resistance, and that is how we find the current. This is what we express. So in this method, we are going to be utilizing this principle by defining branch currents and then applying Kirchhoff's current law to determine the circuit variables. So if we look at the procedure to solving the node voltage method, is first of all, the first step is you define the voltage at each node as an independent variable. Then you are going to, then you are going to select one of the nodes and give it a reference, or select it as a reference node. Usually it is one end of a voltage source and it must be grounded. Then the next procedure is each branch current is expressed in terms of one or more node voltages, like I explained earlier on, and then you use those branch currents to determine or create the number of equations. So the number of equations that you're going to determine are going to be n-1, 1 being that node which is a reference node. And then you apply Kirchhoff's current law at the number of nodes that are remaining except the reference node. You have to identify the nodes like I described earlier on. You have to look at where you have active and passive circuit elements, and then also you have to identify which are the nodes in the circuit. So in this case, we've got 4 nodes. There's node 1, 2, 3, and 4. So this node, the one side of a voltage source is grounded, which we call the reference node in this case, as you can see. And then you have identified the nodes. The other nodes are labeled. This is node 1, node 2, node 3. So node 1 is given a potential V1. You can use letters or numbers. In this case, I'm using the numbers. So V1, V2, and V3. And these are the nodes that we're going to look and find values for. And then we use those node values to determine other variables in the circuit. What you're going to meet are usually 3 scenarios. The first scenario, or the first case that you're going to meet, is when you have a voltage source connected with one reference node and one non-reference node. So in this case, you've got a voltage source connected between a reference node. So this is a reference node because it is grounded, or you ground it, and then a non-reference node, which is node A. So in this case, there's a way that we handle this scenario. Okay, if you have this scenario, you have to consider how to determine the value of VA. So the way we determine the value of VA in this case, which is going to be a known value, it is quite automatic in that when we have a reference node, and if you remember, we're discussing the potential difference between two nodes. So you've got, sorry for that, you've got a reference node and a non-reference node. So where you have a reference node, you have zero potential, and then you've got a non-reference node in this case, which is VA, and then we have the voltage source VS. So the potential difference here is VA subtracting the 0 volts, which is the reference node, must be able to give you the source voltage. So in short, we are saying VA is simply equal to VS. But this depends on where the polarities of the sources are. If the polarities, for instance, the plus is located near or close to the VA, then we consider this as a positive source. If these polarities are reversed, then we are going to consider this as a negative source. But still remains the value of VA will be known in this case. So that's one thing you must bear in mind. So the procedure for us to determine the node voltage method, or applying the node voltage method, first of all is to identify the nodes. We label the node voltages, which is VA, VB, VC, as in this case, and then we choose the direction of flow of current, which is arbitrary choice of flow of current, but you'll be determined and guided by the sources. In this case, the current source, the voltage sources. You know, the current leaves the voltage source from the positive terminal, so it will enter this node, and you have, in this case, we can choose the direction of flow of current to go downwards. But we are not applying this because we know the value of that potential. So all that remains in this case is to find the value of VB. This is the only value that we have to find in this case. That's why I've specifically indicated this flow of currents. And then you simply apply KCL at this node. So KCL at this node, you obtain IX plus IY must be able to give you IS, because we know the value of VA, which is equal to VS for our case. So this is the first case scenario that you're going to meet. And to elaborate this case more, we show you this short way of understanding it. So you're looking at the potential difference between node A and node C, which we know node C is at 0 volts. So since VC is 0 volts, VA minus VC must be able to give you VS, or in short, VA is equal to VS. But if these are reversed, if we have plus minus, and then we have VA, and then we have here VC, then what you are going to have is that our VA minus VC is going to give us minus VS. So in short, VA is going to give us minus VS. That is if the polarities are reversed. So bear in mind, do not confuse the two. And if we go back to now looking at the circuit, since VA is known and what we are remaining with is VB, all we have to do is now create the equation, apply KCL at VB, and create the equation. If we go back to the circuit, you'll find that we have, in this case, IX plus IY is equal to IS, and we have to write these equations in terms of the node voltages. So what is IX? You have to determine what IX is. IX is equal to VB minus VA over R2. that is our Ix, and our Iy is equal to Vb minus Vc over R3. But we know that Vc is equal to 0, and therefore our Iy simply remains to be equal to Va over R3. And since we know that Iy is Va over R3 and Ix is Vb minus Va, which we know Va in this case is equal to Vs, so we replace these variables into our equation, and Is stays as Is. That's why when we come to looking at the equation, then you see that you have Vb over R3 plus Vb minus Va over R2 equal to Is. And we know that Va is equal to Vs. So we replace Va by Vs, which is this replacement, and we can be able to determine the value of Vb in this circuit by using, because Va is known, so what is remaining is just Vb. So we take Vb as and make it the subject of a formula, and we determine what Vb is. So I'm using conductance here, which is 1 over resistance, and you'll be able to determine Vb like so. So that's one stage, and that is case 1. But then when we look at case 2, in case 2, what you notice is that we have, in case 2, we have a voltage source situated between a reference node and connected with a resistor, and then to node A. So in a similar way, we first of all have to identify and define these nodes. So when we come to, we have to define the nodes. In this case, this is going to be Va, this is going to be Vb, this is going to be Vc. After identifying the nodes, one of the nodes is grounded, usually the node that is connected to the voltage source, one end of the voltage source. In this case, this side of the voltage source is grounded. And then, because we have got a resistor between node A and node C, we have to consider that in our calculation. But there are two methods that we use. One of the methods is to create what we call an imaginary node in between the voltage source and the resistor. And the other method is to convert the voltage source into a current source. So let's look at the methods one by one. This is the first method where we convert we add an imaginary node between the voltage source and the resistor. So in short, what we are trying to do is we are trying to create the first scenario. So this is the first case scenario, case 1. Okay, and when we look at case 1, we do remember that if we have a voltage source that is grounded on one side and the other side is not grounded, if we have a potential, for instance here we've got Vd and here we've got Vc, so the voltage source value here is going to be equal to, or the potential at Vd is simply going to be equal to Vs, like we mentioned in the first case scenario. So in this case, our Vd here becomes simply equal to Vs. And now the value of this current that is flowing in resistor 4 here, if we call this I4, the value of this current I4 is simply going to be equal to Vs minus Va over the resistance, which is R4. And this is what you get here. So Vs, so in short, when we apply KCL at node A, which is node A, we've got I4. If we label this as I1 and label this as I2, then what we have in this case is the sum of currents entering a node, which is I4 plus I2, must be equal to the sum of currents leaving that node, which is I1 in this case, I1. And we know I1 is the potential difference between VA and VC over resistor 1. But because VC is equal to 0, what we obtain is simply VA over R1. And when we take this I1 over the equal sign, it becomes a minus. And this is how we formulate the equation for node A. And when we come to node B, it's the same scenario. So we've got I2 here and we've got I3 there. And so what we are saying here is there's a current leaving, which is I2, and I3 is leaving, and we've got IS entering. So the sum of currents that are leaving must be equal to the sum of currents that are entering, which is, in this case, this is I2 plus I3 must be equal to IS. And the equations have been formulated. If we were to, so if I can go through this one again, this is I2, I3 and I. So KCL at node B is then equal to I2 plus I3 should be equal to IS. And this is what we have. So I2 in this case is VB minus VA over R2, which is this one. And then I3 is VB minus VC, which is 0, minus 0, over R3, which is this one. And this is how you solve when you have case 2. This is what we call case 2. So in case 2, this is how you solve it. And you create equations that way. The same case 2, the second scenario is by converting voltage source into a current source. And this conversion, we can convert this voltage source. When we convert the voltage source into a current source, we are going to have a current source parallel to the resistor that it is connected to. And we call this source transformation. And in source transformation, how we determine the value of the current source. The current source is simply going to be equal to the voltage source over the value of the resistor. In this case, we've got resistor 4. So when we convert that, we obtain the current source value. The resistor value stays the same. This method is going to be noticed also when we discuss Thevenin's and Norton's theorem. You can use source transformation. These methods are interchangeable by using this equation. You can also make voltage source the subject of the formula and convert the current source into a voltage source scenario. But in this way, after we convert the circuit, we obtain the current value using IS equal to VS over R4. And then we use this value and this portion of the circuit that we've converted, and we match and add it up to our original circuit and solve it by completing the equations. So when we do that, what we obtain, this is the full equation that we obtain. So we've added, if you notice, this is the section of the addition. This is what we added, what we converted, and this converted section we simply add it to the circuit and we work with it to determine. So it becomes simpler because when you're dealing with current sources and applying KCL, it's much easier. And also you should notice that the node A here, between these two nodes, there's no circuit element, passive or active. This simply implies that this is one node. So then if it is one node, it's simply the same VA as I have shown. So after that, we determine the equations. So at node A, which is this node A, at node A, we have got currents IS2 entering, and if we can label this as I4 leaving, and we can label this as I1, then this as I2, and this as I3. So accordingly to node A, will appear as follows. You've got IS2 entering, which is this one, and then you've got I2 entering, so plus I2. This should be equal to the sum of currents leaving, which is I4 plus I1. And these are the currents that we have. So for I4, which is this I4, this is your I4, we've got VA minus VC, which is 0, divided by R4. And then we've got I1, which is VA minus VC, which is 0, divided by R1, which is this one. And then when we take these over the equal sign, they become minuses, especially this one becomes a minus I2. We leave IS2 on this side. So we've got I2 is VB minus VA over R2. And you have to make sure that here you put the brackets, because this minus sign, when you multiply it with this minus sign here, it becomes a positive sign. So as you expand here, you have to be extremely careful that this minus sign multiplied by that minus sign will give you a plus VA over R2, and this will stay as a minus VB over R2. And that is the way you solve this type of question. Now, when we look at the final scenario that you are going to meet, the final scenario is where you have got a voltage source which is situated in between two non-reference nodes. So when you have a voltage source in between two non-reference nodes, what we are looking at is what we call the supernode method. And in the supernode method, we have got, this is a node A and node B that are not referenced. None of them is grounded. So this implies that for us to determine the equation, first we have to look at what we call inside the supernode. So when we say inside the supernode, this is what we see. We've got VA and VB, VS, which is similar to the first case scenario. And we determine the equation by looking at the potential. So VA is a higher potential because of plus sign, and VB is a lower potential. And that must be equal to the voltage source. So VA minus VB should be equal to VS. And then we also create an equation at the supernode. So we call this equation at the supernode. And this is now taking the whole supernode as a node. And we look at currents that are affecting that node. So we've got a current leaving there, a current leaving there. So if we label this as I1 and this as I2, and then you've got IS, you apply KCL, you've got the sum of currents leaving, which is I1 plus I2, should be equal to the sum of currents entering, which is IS. And this is our KCL. And this is what we create here. So when we come to look at the equation for I1, then we have VA over VC, which we know VC is equal to 0. So VC over R1, and it simply becomes VA over R1. And then I2 is also VB minus VC over R2. That should be equal to IS. And that's the way we handle the supernode type of solution. And yes, so these are the three case scenarios that you meet. And now we'll look at the examples. In the next video, we'll look at the examples. Thank you for watching. Please subscribe to my channel. Good day.